Hi, this is Felix, and today we are going to discuss Wheatstone bridge. It is nothing but applications of Kirchhoff's rule. Wheatstone bridge, it is used to compare resistance and also helps in determining the unknown resistance in electrical network. So first of all, we have to consider a 4 resistor. So here we have to consider a 4 resistor. One is P and another one is Q, R and S. So these are the 4 resistors we are considering, and we have arranged in such a way as shown in figure. Now the corners will be denoted in terms of A, B, C and D. Now between B and D there is a sensitive galvanometer is connected. So the galvanometer is connected between B and D, and this will be denoted in terms of G, and here G is nothing but the resistance of the galvanometer. Now between A and C there is a potential, there is a battery is connected, there is a battery or potential is connected, and this will be denoted in terms of E. Now from this electric field or from this battery we derive a current of I. When the current is meeting at the junction A, that I amount of current is divided into two portions. One is I1 and another one is I2. And this I1, once again when it is reaches B, this I1 is split into two. One is denoted in terms of Ig, the current which is passes through the galvanometer, or we can say the maximum amount of current which is passes through the galvanometer, and this will be denoted in terms of Ig. And another current which is passes through Q is nothing but I3. And here through S, I4, so which means Ig and I2, these two current is combined, and this will be passes through S, and this will be denoted in terms of I4. Now here we have to apply, so here we have to applying Kirchhoff's current rule to junction B. So now we have to apply Kirchhoff's current rule at the junction B. So what is Kirchhoff's current rule? What is Kirchhoff's current rule? The current rule states that the algebraic sum of current at any junction of the circuit is 0. Okay. So now at this junction B, what are the current is involved? I1, then Ig, then I3. So these are the three current is meeting at the junction B. So what is the sum of the current at this junction? It is nothing but 0. Okay, now we have to apply the sine function. So we have to add everything, we have to add summation. But what is the sine function for the three current? So I1 is moving towards the junction. So when the current is moving toward the junction, we have to consider in terms of positive. So we have to use positive for I1. But Ig and I3 is leaving the junction. So what are the current is leaving the junction will be denoted in terms of minus. So now this equation is once again rewritten like this. So I1 minus Ig minus I3, which is equal to 0, and this is equation number 1. The same way we have to apply So applying the same Kirchhoff's current rule to junction. So we have to apply once again Kirchhoff's current rule at the junction D. So at this junction D again the three current is involved. One is I2, then Ig, then I4. What is the sum of the three current is nothing but 0. So now once again we have to apply the sine function. So here I2 and Ig is toward the junction, so therefore both will be denoted in terms of positive, and I4 is leaving the junction, so therefore we have to apply in terms of minus. So this is equation number 2. Next, applying Kirchhoff's voltage rule to loop A, B, D, A. So here we have to take, there is a loop A, B, D, A. So in this loop we have to apply Kirchhoff's voltage law or loop. Okay, so Kirchhoff's voltage rule. So what is that Kirchhoff's voltage rule? It states that in a closed circuit the algebraic sum of product of current and the resistance of each part of the circuit is equal to the total EMF involved in the circuit. So here there is a current and resistor, here current and resistance, here current and resistance. So algebraic sum, product of sum of current and resistance is numerically equal to the EMF involved in the loop. So here in this loop there won't be any EMF is involved, so that here we have to write I1 P, then IG G, then I2 R, which is equal to 0 because there won't be any EMF is involved, so therefore 0. Now we have to use the sine function. So what is the sine function? When the direction of flow of current is clockwise direction, we have to take in terms of positive. So now here I1P is a clockwise direction, then IGG also it is a clockwise direction. So first two term it become positive. And next here I2R, this is moving in terms of anti-clockwise direction. So anti-clockwise direction will be denoted in terms of minus, and this is equation number 3. The same way we have to applying Kirchhoff's voltage rule to loop A, B, C, D, A. So again the same Kirchhoff's voltage rule we are trying to apply for this loop. So here the same rule, the product of current and resistance, the sum of product of current and resistance involved in that loop, which is numerically equal to the EMF involved in that. So here I1P, then I3Q, then I4S, then I2R, which is equal to 0. And in this we have to apply the sine function. So I1P and I3Q, these two are moving in the clockwise direction, so that positive. But I2R and I4S, it is moving in anti-clockwise direction, so that it becomes negative. And this is equation number 4. If Ig which is equal to 0, what is Ig which is equal to 0? So when Ig which is equal to 0, now you can see the diagram. When the potential difference across B and D is equal, there won't be any flow of current through the galvanometer. So at the time Ig it becomes 0. So when B and D experience the same potential, there won't be any flow of current through the galvanometer. So in that condition we have to apply. So in that condition Ig which is equal to 0. Now this condition we have to apply. This Ig which is equal to 0. This condition we have to apply in substitute in equation number 1, 2 and 3. So this Ig which is equal to 0, this condition we have to apply equation 1, 2 and 3. So if you apply this condition in equation number 1, so what is equation number 1? Equation number 1 is nothing but I1 minus Ig which is equal to, I1 minus Ig minus I3 which is equal to 0. Now Ig is 0, which implies I1 minus I3 which is equal to 0. Now this I3 we have to bring it in the other side. Then you will get I1 which is equal to I3. And this is equation number 5. And same way we have to apply this Ig which is equal to 0 in equation number 2. So what is that equation number 2? Equation number 2 is nothing but I2 plus Ig minus I4 which is equal to 0, which implies now Ig is become 0, then I2 minus I4 which is equal to 0. Now this I4 we have to bring it the other side, then I2 which is equal to I4. And this is equation number 6. Next we have to apply in equation number 3. What is equation number 3? I1P plus IgG minus I2R which is equal to 0. Now Ig is 0, 0 into anything the value is 0. So the center term it becomes 0. So what is that remaining? I1P minus I2R which is equal to 0. Now this I2R we have I2R we can bring the other side. So therefore I1P which is equal to I2R. So this is equation number 7. Substitute equation 5 and 6 in equation number 4. So this is nothing but the equation number 4. In this we have to substitute equation 5 and 6. So first of all I1P. So instead of I3 we have to substitute I1 because you have to see equation number 5. So I1 which is equal to I3, and here instead of this I3 we have to substitute I1. So I1Q minus, and here instead of I4 we have to substitute I2. So I2S minus I2R which is equal to 0. And in this the common terms we have to take it outside, so which means I1, and here P plus Q you will get minus of I2 S plus R which is equal to 0. Now this term we have to bring it to the right hand side. So I1 P plus Q which is equal to I2 S plus R. So now this is equation number 8. Now you have to divide. Okay, so divide equation 8 by 7. So this is the 8th equation and this is the 7th equation. So we have to divide this. So now I1 P plus Q divided by I1 P which is equal to I2 S plus R divided by I2 R. So here I1 and I1 and here I2 get cancelled. So what about the remaining value? So next simplify P plus Q divided by P, which is equal to S plus R divided by R, which implies P divided by P. We have to split. So Q divided by P, which is equal to S divided by R plus R divided by R. So here P, then R will be get cancelled. So what about the remaining? So 1 plus Q divided by P, which is equal to S divided by R plus 1. So this 1 we can bring it to the other side. R 1 will be get cancelled. So the remaining terms you will get Q divided by P, which is equal to S divided by R. So taking reciprocal of this, okay, so P by Q, which is equal to R by S, and this is nothing but Wheatstone bridge condition, or we call this is nothing but bridge balance condition. So this is nothing but bridge balance condition, and by using this we can try to find the unknown resistance of the resistor. So here we are going to discuss with one example how we can able to find the unknown resistance. So here we are considering P, which is equal to 100 ohm, Q, which is equal to 1000 ohm, R, which is equal to 40 ohm. So here they have given one of the condition. Galvanometer shows zero deflection. Zero deflection means Ig, which is equal to 0, which means in a Wheatstone bridge, junction B and D, it maintains the same potential. So it is denoted Ig, which is equal to 0. And here we have to try to find the S value. So what is the bridge condition? P divided by Q, which is equal to R by S. So what is the value of P? P is nothing but 100 divided by 1000, which is equal to 40 divided by S. Okay, so now which implies 20 and here 20 get cancelled. So which means 1 divided by 10, which is equal to 40 divided by S, which implies, and rearranging this S we can bring it to the left hand side, and 10 we can bring it to the right hand side. So therefore S, which is equal to 40 into 10, so which means S, which is equal to 400 ohm. So like this we have to try to find the unknown resistance of the resistor which is involved in the circuit. Thank you.